Hello and welcome to part 3. Part 3 will be looking in a little more detail at these peaks here. At certain values of Q, certainly large values of Q, we do see this case where the output voltage can be bigger than the input voltage. We're getting positive gains expressed in dB terms. The circuit is showing voltage gain. Interesting question to ask. At what frequency does this maximum value occur? And it's a bit long-winded algebra, but you can derive it fairly easily, starting from the standard formula for the gain expressed in terms of the resonant frequency and the Q factor. And that's this. Right, if we want to know the maximum value of the gain, then we're interested in the magnitude of the frequency response. We're not so concerned about its phase at the moment. So let's just worry about the magnitude. The magnitude of 1 is just 1. The magnitude of this is going to be varying with frequency, and that is what will give us the peak. Now, if we want a maximum value of h of j of omega, where the numerator is clearly constant, we must have a minimum value of the denominator. So what we're interested in doing is finding the minimum possible value of this. We want a minimum. Right. First thing to do is to note that this can be expressed as the sum of a real part and an imaginary part. The real part is 1 minus omega squared over omega naught squared, because j squared is minus 1. The imaginary part is j times omega over q omega naught. And now Pythagoras could come to our aid and give us an expression for the magnitude of this complex expression. If I were to plot it on an Argand diagram, I would get something like a point there, where the distance along the real axis is the real term, and the imaginary component, the distance from the real axis, is omega over q omega naught. And that would be this term. The magnitude of this term is the length of that line, and Pythagoras will give us an expression for that. It's the square root of 1 minus omega squared over omega naught squared all squared plus omega over q omega naught all squared. And I'm looking for a minimum value of this. Well, if I want a minimum value of the square root of something, I want the minimum value of the something. So that's going to occur where this has a minimum value. Where does that have a minimum value? Well, standard technique for finding the minimum value of something is to differentiate it and then put the differential equal to 0 because we're looking for a turning point. So we'll differentiate this expression with respect to omega. And that would give us this, 2. 1 minus omega squared over omega naught squared, multiplied by the differential of what's inside the bracket, which would be minus 2 omega over omega naught squared, plus the differential of this term, which would be 2 omega over q squared omega naught squared, and that has got to be equal to 0. Right, next step. Let's take this term here over to the other side of the equal sign, and that would give us 2 omega q squared omega naught squared equals 2 omega over omega naught squared times 2 times 1 minus omega squared over omega naught squared. And 2 omega cancels with 2 omega, omega naught squared cancels with omega naught squared. That's looking a little bit nicer. We could then take the 2 down here, and that would give us 1 over 2q squared equals 1 minus omega squared over omega naught squared. Almost there. We'll take this term over here and this term over there, and we'd end up with omega squared over omega naught squared equals 1 minus 1 over 2q squared. In other words, omega squared equals omega naught squared times 1 minus 1 over 2q squared, or omega equals omega naught times the square root of, and I could express this term by taking the 2q squared up to the top as well, so it's 2q squared minus 1 over 2q squared. Note that for large values of q, where 2q squared is much, much bigger than 1, this will mean that omega is approximately to omega naught for large q. For big values of q, the maximum does occur at or very close to the resonant frequency, but for smaller values of q, the maximum is actually at less than the resonant frequency, slightly before you get to the resonant frequency itself. Now, there's something a little interesting that's hidden in this equation, and that is this frequency here, we know it must be real, which means that this term here must be real, which means that 2q squared minus 1 must be greater than 0. Otherwise, we're not going to have any real frequency that would give us a maximum. And that means that q squared has got to be greater than a half, or q greater than 1 over root 2. If q is greater than 1 over root 2, then there is a frequency at which there is a maximum. If q is less than root 2, 1 over root 2, then there is no frequency at which we have a maximum in our frequency response. It just decays all the way from 0. That's why I picked 1 over root 2 as being our next interesting point. It's the value at which you could say that there's a maximum value at omega equals 0 at DC. Or you could say it's the largest value of q at which there is no peak in the response. I think it's a matter of semantics which one you say. But for values of q which are greater than 1 over root 2, there will be a maximum at some finite frequency in the amplitude response. For values of q which are less than 1 over root 2, there is no maximum. It starts from 0 and it starts decaying straight away. For q equal to 1 over root 2, it starts off horizontally. You can't really see the effect, but for q greater than 1 over root 2, it does actually start off going up, very, very slightly up. For q is less than 1 over root 2, it starts off very, very slightly going down. For q is equal to 1 over root 2, it starts off horizontally. That's why the maths is telling us there is sort of a maximum point at 0 hertz. And then it heads off. But it never gets higher than it was at 0 hertz. These should all sort of tail off and end up going down at the same point. Q equals 1 over root 2. They all asymptote to the same final straight line. Right, so that's the value of q of 1 over root 2. If you go through the maths, you'll find that those poles are here. at omega naught over root 2 times 1 plus or minus j. They're at 45 degrees to the real axis. This is one of those things that sometimes trips people up. It means that if you have complex poles, it doesn't necessarily mean there is a maximum. If you had a value of q that was slightly less than 1 over root 2, the poles would still be complex, but you would not get any maximum. This is what they look like. At this critical q factor, there is just no maximum, no peak in the response at all. But the poles are complex. Finally, actually I'm not sure this finally one will fit in this YouTube clip, so I think I'll have to do a part 4. See you in part 4.